This video has been made possible thanks to the sponsorship of ElectroRent and Keysight Technologies. Greeting Earthlings! If you follow the channel, you know that we love all things Apollo, and that during our last visit to Steve Jurvetson's amazing space collection, we were given the opportunity to take 2 holy boxes of Apollo electronics to our lab. These are the boxes that brought you voice, data and live TV from the moon, and should be early masterpieces of microwave electronics, the blackest of black arts in analog electronics. We left the last episode with our NASA Golden Transmitter almost fully characterized, but not quite. We're still missing the phase modulation sensitivity measurement. But in the meantime, a promising pile of Keysight equipment had accumulated, loaned to us by Electro-Rent. In there should be a specially equipped modern signal analyzer that should allow us to complete our missing measurement, and much more. So today is a good day because we have a visitor.
My name's Steve Case.
And tell us what ElectroRent does.
Well, first off, I'm a fan of the channel, so I'm familiar with what Mark does here, and also a fan of all things Apollo.
Yeah, you actually worked with Mike Stewart and did the transcription of the
I did some transcription
listings.
of some listings back for the virtual AGC project.
Right. So Steve forgot to say what ElectroRent does, but you guessed it, it rents out the latest and greatest of test equipment, including lots of Keysight test instruments. And the Keysight internal marketing demo units are in such high demand that even Keysight had to request the help of ElectroRent to find some for us for a longer term loan. This is equipment that would usually go to real paying customers, so we are very grateful to ElectroRent.
And when you put out the word for some help with modernizing your test equipment, we kind of found out. So here we are. So let's start out. Well, should we bring it in?
Actually, yeah, we were just joking that today is my birthday, and I got lots of birthday presents. So what is it that you brought?
So what we've got here for the spectrum analysis is a Keysight N9020B MXA series analyzer, also known as the signal analyzer because it has high-speed demodulation capabilities with bandwidths way up into the
right, and that's really what I was after, because right now we are at a point of the project where we want to go behind just the unmodulated signal, and it is just going to be all modulation analysis in this weird phase format.
Right. We're going to be utilizing the analog demodulation application to help us with the demod.
Right.
Right. The other thing we've brought is the an EXG vector signal generator, which is the N5172.
Yeah, I'm losing it with the numbers too on the old HP stuff.
It's going to be able to generate phase modulation.
Right, very controlled. And this is basically the grandpa of that one, right?
Right. Then the other things that we have are the arbitrary waveform generators. What we had on hand were these 33522Bs, which are dual channel ARBs, which are going to take us out to 30 megahertz on each channel. Yeah. So we'll be able to use those to generate some of the modulation.
Cool.
So happy birthday.
Oh, thank you. I feel honored. Well, thanks ElectroRent and thanks Keysight. Perfect. Big logo. Oh, it has windows on it. That's scary. That is very scary.
Don't worry, it's okay.
It's fine. You sure? Well, welcome to the 21st century. Whereas my vintage HP analyzer just switches on and goes, This one takes a good 10 minutes just to call Papa Bill Gates and search through its Keysight licenses. But I digress. Alright. So in this video we are mostly going to go from Keysight equipment to Keysight equipment, setting the microwave generator to mimic an Apollo S-band transmitter and the analyzer an Apollo S-band receiver. So basically they will be our Apollo reference ground station, which either of them can do without even breaking a sweat if given sufficient time to boot, that is. First, beginner steps, set the generator to 2.1064 GHz and receive it on the analyzer, which takes a surprising amount of menus and submenus, but I digress again.
Yeah, the one, where is it now?
Yeah, there are so many things.
Like this one.
Auto tune.
I'll do it just for fun.
For effect. Oh!
See how nice it is?
Yeah,
But what did we do?
I don't know.
Of course, I don't know either. No, I'm just saying. But yeah, it just kind of obscures, you know, your knowledge of what all these things can do.
But we soon got it going, and while both of us old farts were grumpy about the clunky and somewhat unpolished software preventing us from enjoying the good hardware underneath, we were quite happy to take the modern performance and flexibility to the bank. We had our first end-to-end transmission experiment set up in no time. So our warm-up assignment was to recreate what was called the emergency voice mode. This form was actually only used in the downlink direction. The emergency downlink voice transmits just voice and nothing else, and is similar to regular radio. It came in handy during the Apollo 13 mission. In this mode, you start with the regular S-band carrier. We'll use the uplink frequency at 2.1064 GHz. Then you modulate the voice right on top of it using phase modulation. On the spectrum analyzer, it will look like a fattening of the transmit line as the instantaneous frequency wiggles around with the voice. Then that's it, you just transmit it. You pick your disabled spaceship signal on the other side, and if one of their two redundant PM transmitters still works, you should get the same signal, hopefully. Then you just do phase demodulation to extract the signal and get what is called the baseband in RF jargon, now at voice frequencies in the kilohertz range. And that's it, it should be the voice. Hopefully you can hear it, because if not, your next best move is Morse code, which was also supported. Note that the only difference with a regular radio is that this is transmitted at microwave frequencies, and that the modulation format is neither the usual AM nor FM. It's this unusual analog phase modulation, which they were forced to use because of the Doppler ranging. Now, to replicate this with our Keysight equipment, it's almost laughable. It's the bozo filter experiment, just to make sure we can press the buttons and find the hidden menus. We start with the arbitrary waveform generator. Since it's arbitrary, we stuck pre-recorded digital voice in it. Then we use the EXG generator and connect the output of the ARB to one of its external inputs. Now, since we have the phase modulation option on this EXG, all we got to do is to set it up at 2.1064 GHz and external PM modulation, and it's done. To receive it, we use our MXA. We could connect the two via antennas, but we didn't even bother, we just use a cable. And since we also have the analog demodulation license on this MXA, all we got to do is to set it to 2.1064 GHz and rummage through enough hidden menus to eventually find how to turn the demodulation on. Conveniently, there was a speaker output, so we used that. And that's it. Told you, it's a bozo filter of an experiment. So, Steve has set up a little demo of a whole transmission link on Keysight equipment.
We have the modulation saved on the Keysight waveform generators, and we're actually sending it into the modulation into the generator to generate the 2 gigahertz, 2.106 gigahertz signal.
Right. It's
and then we're
right here at the moment.
Get to look at it first. Let's take a look, and we can see that the arbitrary waveform generator plays a waveform for us.
Can you do it again? So that's PM modulated. That would be update of voice, but emergency without the sidebands, right? When they run into trouble, they get rid of all that complicated sideband, and they just modulate it on the baseband. That's what they did on Apollo 13, actually. Save
Right.
some power.
So
And
now,
you can actually demodulate it with the equipment?
yes. So what we're doing here is we've got the demod application running, which has the ability to send the audio out to some speakers that we have. So here we go.
Apollo 12 Houston, try SCE to auxiliary, over.
So it sounds rather simple. So what we're hearing is it being played through all the way,
The whole link.
the whole link.
PM mod,
Apollo
PMD
12
mod.
Houston, try SCE to auxiliary, over. Apollo 12 Houston, try SCE to auxiliary, over.
There you go, piece of cake.
Piece of cake. That analog output is coming out of the analyzer, the signal analyzer, and going into the scope.
Right, so we can further process it if we had the subcarriers and the FM modulated stuff.
And I think we're ready to try real hardware.
Okay. But that was just the warm-up. Now we are getting serious about flying to the moon and want to build a full uplink with voice, data and ranging all at the same time. And as we had seen in episode 10, this gets complicated rather quickly because we need subcarriers. We'll sure need an extra dollop of elevator music for that one. Here we go. We'll build our voice circuits in this corner first. We start with a subcarrier at 30 kHz, which is just a big name for a sine wave. We then modulate the subcarrier with voice from Capcom. This is done using standard FM modulation. The carrier will be fattened up by the modulation and will look something like this on the spectrum analyzer. Next, we'll build our S-band microwave link. We generate a 2.1064 GHz carrier, then add the voice subcarrier to it. This time we use PM modulation. So the resulting modulation stack is voice on FM on PM. As we saw in episode 10, this results in a spectra with sidebands on either side of the carrier. If you were to zoom in on a sideband, you'd simply see our fattened FM modulated voice subcarrier. So far, so good, we've got voice. But we want to transmit data at the same time. And for this, I'll need an extra sheet of virtual paper. I'm afraid it's going to take the whole page. We start with our digital message, which is a 30-bit long pulse code modulation message, or PCM, which once again is just a big name for 30 raw serial bits. The serial bit rate is very slow at only 200 per second. Then we code each bit with 5 sub-bits to protect against errors. That bumps our rate up to an amazing 1 kilobit per second. Then we generate a 2 kHz sub-carrier. Again, just a big name for a 2 kHz sine wave. We modulate it with our bit stream, this time using phase shift keying modulation, or PSK. Phase shift keying is the digital equivalent of analog phase modulation. You modulate the phase of the carrier with big discrete jumps of 180 degrees. This gives this funny waveform at the output. It might look weird, but this is a very efficient digital modulation format and very easy to decode with simple electronics. Then we generate another 1 kHz subcarrier and we add the two together. I could not draw the result, so I took the waveform from an original NASA drawing. Once again, weird to your eyes, but this is done to simplify the decoding electronics on the spaceship. Next, we generate a 70 kHz subcarrier and use FM modulation to add our data signal. We again get our flattened subcarrier with all the data in it, which we send back to the other page. Here it comes, and again we use phase modulation to put it on our microwave link. This generates two additional sidebands separated by 70 kHz from the carrier. So our final modulation scheme for data is PCM on PSK on FM on PM. You guys still with me? Because we're not done. We have not done the ranging signal yet. I won't go into too much details about this one because it'd take another 10 sheets. But all you need to know is that we need to add a digital code to our carrier, which is a carefully generated pseudo-random noise. It's pretty fast compared to the rest at 1 megabit per second. For this, we use no subcarriers. We modulate it straight onto our carrier using analog phase modulation once again. This will add a wide noise floor to our spectrum, all the way at the bottom. And that's it, ready to ship. Off to the antenna and into space it goes. Phew! Now, this is nothing compared to the complexity of even the first generation of cell phones, but still, in 1965, this installation required a huge pile of electronics. But let's reproduce this with our modern Keysight equipment. For the green voice circuit, it will just take a dual channel ARB. Channel 1 set to 30 kHz, modulated by channel 2, which will play the digital voice. Modern piece of cake. The yellow microwave part does not change, our EXG generator will take care of it. The data will take two more of the ARB generators. The first one will have channel 1 generate the 1 kHz sign, while channel 2 will do the 2 kHz one, PSK modulated by the external digital source. We will only use one channel of our second ARB for the subcarrier, FM modulated by the output of the first ARB. We won't yet hook up the ranging code this time around, but Master Ken has already implemented the Apollo pseudo-random ranging code on the TNC 4.1. That's it, that's all we need to reconstruct our full Apollo uplink with modern test equipment. Let's try it out. So, we have been doing good work with Steve here, and we have reconstituted our Apollo ground station with Keysight equipment, and it's now transmitting the correct way both voice and data. So this is up voice and data to the spacecraft.
Right. Of course, this is simulated.
So the way this is done, maybe I'll simplify it. Try turn off. It's so complicated. I'm getting lost in it. So, okay. So I've turned off up data, and let's turn off modulate. It's getting complicated because there's two oscillators in each of those. There you go. And then we turn off this one. I'll show you how it's done. Because the first thing is that there would be on baseband, there would be the ranging code, and that we don't have yet. But after you've done the ranging code, you are going to send a voice subcarrier, and there it is. Then to transmit the voice, you would FM modulate this carrier on. There you go. And then we have our FM modulation.
And what we're looking at is the arbitrary waveform running in a loop.
Right. This is the Apollo 12 message,
yeah,
going up and up and up and up. So let me turn that one off for a second. I'll just go one, output off. So there is another subcarrier. Now we are going to add data ups, and that's the basically the command box that Ken was working on, and we have it simulated here. So it's on a carrier which is now at 70 kilohertz, and now we modulate it with the instrument on top. So if I go modulate on, there we go, and it's all very low bit rate. It's actually 1 kilobit per second, so you kind of see it wiggle in FM.
Right.
And now it's transmitting just once at this point. And so if I get my voice in, there you go.
Now we have both.
We have both. So that's actually the stuff that will be received on the other end. And the same thing, we'll have to deconstruct it. It took a whole building to do that on the ground in the 1960s. It's still pretty mesmerizing to see it. So you can see the data wiggling about and the voice, and nothing happening to the carrier, and that's on purpose, right? That they went through that complicated scheme doing the phase modulation because they wanted to keep the carrier smacking, because we are going to measure the Doppler with that carrier. So it's super important that it stays there. So our job will be to receive it and demodulate it on the other side. And one more thing I wanted to do with Steve with the MXA is to finish the measurement of our NASA transmitter from the last episode. We need to measure the phase modulation rate, which the analog demodulation option of our MXA should do in a few minutes. There it goes, and then I'll modulate it at 70 kilohertz, and we should see the phase modulation coming through. It does. And then Steve, you have to work your magic and get the spectrum analyzer tell us how many radians in phase it's going to be in there. So
we're running analog demod?
Yeah, analog demod should do it. Oh yeah, I see it. It's coming up here. So that's the demodulation auto scale. Steve told me to use the auto scale button. It actually does work. So it's demodulating our signal, and then it should tell us the peak milliradian. Yeah, it's about, so it tells us right there. We have the measurement we want. The max tells us 400, this tells us 365. So that's the measurement we wanted. Thanks a lot, Steve, and thanks ElectroRent for doing that. And you guys, if you have some RF equipment or test equipment to rent, go to ElectroRent.